Okay, hello everybody. I'm Mike Walmsley, connector guy for the last 40 years, working in various engineering and product management roles. Connector industry is kind of interesting. Once you get sucked in, it's really difficult to get out, so that I'm still here. But it's been really interesting working in the defense market the last 12 years. There's been a lot of development and standardization of new technologies because of higher speed, emerging applications, higher density. And if you look at the active study groups that are within VITA today, it's going to be really interesting in the next few years because as we look at next-gen architecture. So it's an exciting field to be in. What I'm going to talk about today is high-speed video and how the interconnect solutions are evolving and the standards are following and supporting it. So some of the trends in video processing, there's an increased demand in situational awareness. You think unmanned vehicles, surveillance requirements. It creates challenges for the video stream, for the video data. So there's more complex video signaling from multiple sources, higher resolution imaging. There's still a lot of 1080p applications today, but 4K is emerging and on the horizon. There's missions that require active video feeds, live video, which creates bandwidth challenges. There's also requirements for low latency and high fidelity, which at times can require a balance between them. And from an architecture standpoint, there's always the efforts to process closer to the sensor. There's higher speed protocols that are being utilized for video data transmission. And there's the drive toward open standards, which we've heard a lot about this week. So if we look at some of the video protocols, these are actually being added into VITA 65 for open VPX slot profiles. But the first two, STANAG 3350 and RS170A, are composite analog protocols that require coax cable, really not high speed, and be supported by legacy designs. But then you get into the digital interfaces like SDI, serial digital interface. There's different speed levels up to 12 gig SDI. Co-Express, which runs over a coax cable, has speeds up to 12, CXP12, which is 12.5 gigabaud, uses coax cable and has the capability to run power over the coax cable. So you could power a camera using Co-Express. And ERIC 818 was really developed for high bandwidth for avionics applications, up to 28 gigabaud. There are different levels. And you can run variant 818 signals over copper differential pair or over actually a single fiber, so very high bandwidth. So if you just look at the basic elements of video processing, you've got cameras, you're capturing the data at those sources. You've got a processing box, basically. You're doing processing, it could be encoding, compression, or AI inference, or fusing multiple data streams together. There's a lot going on in that chassis. And then you get out to the display, or the output. So I'm going to talk a little bit about the areas, what's inside the box from an interconnection standpoint, and what's the external outside the box, what options we have and what's being developed. And obviously, the latency is very important. So from the time that video is captured to the time it's put in the output is very critical for our missions. So keeping that latency low is a key part of the processing requirements. So this is an example from Wolf Advanced Technology. So Wolf has a focus on video processing. We've worked with them quite a bit as a company, and they've also been active in the VITA and SOSA standards. So this shows a 4-slot chassis. Essentially, it's, you've got a single board computer. You've got a sensor card. This says an RF sensor. It could easily be a video card, a fabric switch, and a GPU card for processing. So here you've got a direct link in this specific case between the sensor card and the GPU. So you've got 8 lanes of PCIe that can transfer over the VPX connectors to get the data to the GPU for processing. But you'll notice the payload cards at the bottom, sorry, I'm trying to find the pointer here. These little blocks here, those are the after blocks that can be filled. There's some mention of those previously. Those can be filled with optics or coax or a combination of both. So there's that added capability within those slots to process data on coax cable or optics. So if you look at what 65 has today, 65.1 is where the slot profiles are defined. It's where the connector apertures are defined. There's half apertures, full apertures, 1.5 size apertures. There's coax only, there's optics only, there's hybrids that include both. So the system designer has some choices. They are standardized, but there are different options depending on what the requirements of the application are. But if you look at the coax interfaces, the SMPM was the original one. SMPS and NanoRF were added to the 67.3 standard in 2017, I believe. Those are higher density solutions, so you can get more contacts in a smaller space. But they're all 50 ohm. They're all 50 ohm interfaces. So as we get into those higher speed video architectures, having a 75 ohm impedance matched contacts becomes important from a signal integrity standpoint. So we've developed and are launching a 75 ohm nano RF product, basically taking what was done with a 50 ohm nano, scaling it to a true 75 ohm impedance, using all the rugged guide features and the capabilities that we developed with the nano RF into a 75 ohm true impedance match solution. And the modules that are shown in the bottom right, you've got inserts that include 6 video, 75 ohm contacts for video, and you've got an MT. So you've got that hybrid solution where you can handle any of those coax protocols, or you could run ARINC 818 through the fiber or use it for Ethernet. So looking at how that looks in a slot, you've got typically, you've got your VPX connectors where you've got your P0 with your power and utility signals. You've got discretes in there. You've got high-speed differential pair going through the copper solution. And then you've got the aperture. And what we've done with the 75 ohm nano RF is develop that around the 66.5 standard. I know there's a lot of standards, but this takes it to a point where that MT location matches everything that was previously done with Vita65. So you could have an edge-mounted transceiver right on the edge of the card at that MT interface, or you could cable it to a mid-board transceiver. So very versatile. And the other thing we've done is we've laid out those 6 contacts and an MT into a VNX Plus. So Bill talked about VNX Plus. We've laid that out into an aperture for VNX Plus applications as well. So going back to a Wolf example, this is their video processing unit that they've developed. You could see in the schematic in the P2 position, you could see the coax contacts there. You've got 12 total coax contacts and 2 MTs. The slot would look something like what's on the right there, our image. So here they've got 2 12 gig SDI inputs, 2 component video inputs, and then 4 12 gig SDI outputs, all running through the coax. So a lot of capability there. And you've got the 2 MTs, so they could use that for ARINC 818, you could use that for Ethernet ports. So if we get outside the box now, look at the panel of the chassis and the cabling running out. There's high-density coax solutions for 38999 connectors. So when I started in the industry, this product was there. I think the standard was developed in the 70s. It's a size 12 coax contact for 75 ohm cable, and it was mechanically attached to fit to 75 ohm cables like RG179. But the contacts aren't impedance matched. If you look at the standard, those contacts are designed to a specific structure of the contact and the outer contact and the interface, and they're developed to match into 50 ohm cable, 75 ohm cable. There's really no difference between them. So because they're not matched, you get more losses, more reflection back from it, more of those speed bumps that Ivan was talking about yesterday in terms of signal integrity. So you're limited to a frequency of 3 gigahertz or maybe less in some cases. But it serves a lot of the composite video protocols, and it's been standardized around the J3 connector in SOSA. So it does support some of the video applications of today. But as you get into higher speed, there's a 75 ohm impedance match size 12 contact based on the SMPM interface. So this takes what we've done in 50 ohm SMPM, very tight tolerance, from a signal integrity standpoint, it's made sure that structurally throughout the connector, It's impedance matched. It's designed for 75 ohm impedance and performs very well to 20 gigahertz and higher. So those are also size 12 contacts, so they fit in the same standard inserts of 38999s, and those are getting adopted into standards today. When we look at optical outside the box, MTs have a lot of bandwidth and density, a lot of fiber density within a very small space. But there are single fiber termini that are currently today, again, in the J3 standard that are called out. So there's a physical contact and expanded beam or lens beam options, single mode, multi-mode, and they fit into standard size 16 cavities. If you need more bandwidth and more density, VDA87 connectors are specified within the SOSA standard today. So it's a significant density increase, a lot more fiber count. We really technically can go from 8 to 48 fibers. 48 fiber ferrules aren't very common in industry today, but they're starting to emerge. 12 to 32 are most common. 12 and 24 for physical contact, and 16 and 32 for lensed. This chart shows all the different MT configurations that are being adopted into the VDA87 standard. You can see that there's 3 different connectors there. Those are different sizes with a single MT, 2 MTs, or 4 MTs. And the advantage here is you could take an MT, run ARINC 818 through it. You could assign other MTs for Ethernet. So you could consolidate some of the optical requirements going outside the box. 75 ohm coax cables. Again, when I started in the industry, this view on the left is what we had. We had a legacy MIL-C 17 RG59 cable with a single braid, less than 95% coverage, braid coverage, 1 gigahertz, solid polyethylene dielectric core, minus 40 to 85C. What's shown on the right is a Gore cable designed specifically for 12 gig SDI. And you can see that it's got different layers of shielding. It's got that helical wrapped silver-plated copper outer conductor for excellent shielding. It's got a very thin jacket for flexibility. It's got expanded PTFE dielectric, supports minus 55 to 200C. So there's been a lot of developments over the years for cables for 75 ohm for video, but there are some very nice solutions being targeted for those higher speed protocols today. The bottom is the conformable cable. So when we developed the nano RF inside the box, there's some pretty tight packaging requirements. We needed something very small to keep that density within the module. So we chose a conformable cable, which is essentially a tinned outer braid. It's hand formable, is easy to route, and it's available from multiple sources. So it's a commercially available cable that can be bought off the market and performs extremely well. So we use that for our nano RF modules. The example on the bottom right is actually a 50 ohm solution where Annapolis Micro is running cables through a plug-in module. So in the plug-in module, you're running cables around components, around heat sinks, et cetera. So routing becomes very critical. So the conformable cable really fit the need for what we needed for the 75 ohm nano RF. So I'm going to go through just quick. So the standardization is always important. We talked about interoperability. So anything that we do that supports these applications, any new developments, we want to make sure that they get into a standard where the interfaces are defined, the requirements are the same. So anybody's connectors or anybody's equipment can plug into anybody else's that follows that same standard. So on the left side, camera interfaces, there's 75 ohm BNCs, there's 75 ohm high density BNCs, there's DIN connectors. Those all have standards around them. They're relatively standard interfaces, and the cabling can come from multiple sources. The chassis interfaces, I talked about the 38999 solutions. Those interfaces, both the coax and the optics, are being defined within relevant standards that are listed. And then for the slot profiles, in 65.1, 65.0 is where the overarching OpenVPX standard is. So we've added those protocols in with Greg Rocco's support, or we are adding those. In 65.1, we're adding new slot profiles to include those 75 ohm nano RF blocks with the optics in it. So somebody building a video processing card like the Wolf example, they can pick that slot profile. They have got a common interface that they will use. And then those standards on the right, 67.3, 66.5, those cover the RF and optics within the OpenVPX architecture, the actual interfaces for them, and Vita46 obviously for the entire slot. So just summary, demands for higher resolution imaging and processing is really driving some changes in the industry. Video protocols have evolved and they're being more widely used. You're starting to see more high speed, higher speed, even higher than 3 gigabaud today, being designed into new systems. And then new developments in interconnects are following. And then the standardization is being worked around that. So we're making sure that those solutions exist, they are interoperable, and they'll be around for many future generations. So thank you for your time. Any questions?